Hi everyone, welcome to the session Geospatial Analytics at Scale with Big Data Toolkit. My name is Kyunam Kim. I am the product lead for Big Data Toolkit and I lead Advanced Spatial Analytics team in Professional Services. Joining me today is Alex Armand. Alex is a software development engineer working with me in the same team. Before we start today, I want to take a moment to say thank you all for getting through the year 2020. Thank you for staying healthy and thank you for attending the Dev Summit this year. Because of this unique situation we are in, I'm sure many of you, as a GIS professional, as a data scientist, as a developer, I'm sure many of you are working on analytics work related to the COVID-19 pandemic crisis. I am hoping all the powerful capabilities and tools you're about to see today can be utilized and somehow contribute to your analytics workflows to support our communities to get through this difficult time. Big Data Toolkit is a soft solution from Professional Services. If you have any technical questions, business questions, and even if you want to set up a meeting with us to discuss potential proof of concepts for your use cases, please contact us at this email address. Big Data Toolkit runs anywhere where Apache Spark runs. It can run in Azure Databricks, HD Insight, AWS EMR, AWS Databricks, Google Cloud Platform, and Cloudera Platform. I am using Databricks in Azure today, and you will see how ArcGIS Platform can be integrated side by side where you can take your analytics to the next level by leveraging or to leverage a rich set of advanced spatial analytics tools available in ArcGIS. So let me give you a quick tour of the cluster that I'm using today. I have a small cluster which has 3 worker nodes, and each worker node has 256 gigabytes memory and 64 cores. And then, first thing that I do, I import every packages classes that I need, and first I activate Big Data Toolkit with a proper license file. And then I specify path to my input data set, path to my output folder, a couple of handy utility method, and I have schema information. As a starting point today, I am using New York City trip record CSV files, and I just defined the schema information for that. So it has this many columns, and each column has these data types. One thing that I forgot to mention, to use BDT, only thing you need to know is how to compose SQL statements. And if you like, you can use Big Data Toolkit with Python and Scala. But for today, I am using Scala. But for the second part of the presentation, Alex will show you how to use Big Data Toolkit using Python in ArcGIS Pro Jupyter Notebook. Now, let me resize the browser to this way so you get to see both platforms in action. So, Big Data Toolkit operates on data frames. And you may wonder how we're going to handle geometry aspect shape columns. if you're ArcGIS user, if you open up the attribute table on a feature layer, you see this shape column, right? We follow the same convention, meaning in the Spark data frame, we add shape column as well. So let's bring the data in. I'm telling Spark, go read my CSV file sitting in my distributed file system path here. It is comma separated. Yes, every CSV file has header row. And knowing this New York City area extent information, I want you to do some cleanups for me. So only retain, based on drop-off location, only retain the records that are within this New York City area. In the end, I am asking Spark, go pick up my BDT function from XY, which will take longitude and latitude value, and it will give you the shape geometry information back. And I am adding unique identifier on each point row. So if I visualize that data frame, I get to see all the original taxi attributes plus the new shape column, which is nothing but a struct column that has well-known binary information and a little bit of extra information that will become handy at some point, which is nothing but bounding box information. Now, we are dealing with 34 million taxi trip records. So that's taxi. Now you say, oh, I have my GIS dataset in file geo database. What do I do? Nothing. Just put them on your distributed file system and use built-in BDT component called source file geodatabase and tell it where that file geodatabase is, what feature class you want to read from, and what fields you want to retain. And then finally create a shape column that will represent polygon geometry. Again, the content of that data frame is with original feature class attributes, and you get to see shape information or column gain as well. So key takeaways. You don't have to do anything with your GIS data set. Just use them as is. We are not requiring you to turn them into some kind of special format. Plus, you don't have to index at all. Just put them in. We are not requiring you to build special indexing for you to do the join operations and any other GIS operations. And plus, we have many other ways to read and write your GIS data in and out of your cluster. So if your data set has a column with well-known text values, we have a function to read that well-known text value and give you back geometry information. And same logic goes with well-known binary. And if you have your data in shape files, we have a component that can read those shape files from your distributed file system and give you back data frame. And we can do the same with enterprise geodatabases such as Postgres, SQL Server, and Oracle. Now, I have persisted taxi data set into Parquet format for the later demos down the notebook. So you may ask, what functions does Big Data Toolkit provide? If you ask Spark, list me all the functions that you're aware of, it will show you all the built-in Spark functions first. And then if you go down to the list, you will start seeing st underscore function name. So st stands for spatial type. So we ship spatial type functions with Big Data Toolkit. So for example, we have buffer functions, centroid functions, and many spatial relationship related functions like contains, crosses, disjoint, touches within, all kinds of spatial operations. If you pick a function and you want to see more detailed information out of it, you can use extend keyword, meaning you can ask Spark, describe me buffer function in more detailed manner. Then it will tell you, oh, this function takes these parameters, and this is how you will use in SQL statements. One thing that I want to highlight, Big Data Toolkit functions are not user-defined function. They are catalyst expression, meaning let me explain this way. User-defined function is kind of black box to Apache Spark. They don't know what your intention is in your function. So in a way, they cannot optimize for you. But us, by extending catalyst expression, we can kind of hop on built-in planners, strategies, and optimizations so we can get more performance out of it. So if you Google search Apache Catalyst expression, and if you read Project Tungsten, you will understand what I just described. So let's buffer a little bit. So let's read text strip records from file system, and each record has already shape column in it, and I am taking that and I'm giving it to buffer function, and I'm asking use this radius to buffer a point. And by the way, point is in 4326 spatial reference ID. So if I execute this and go to the other side, refresh, now buffer table showed up, drag and drop, finish. Now I see a bunch of buffer polygons or rings. So that was pretty easy to persist to ArcGIS platform for you to visualize what you have. I think I mentioned this earlier, but again, you can use Postgres, SQL Server, Oracle, and ArcGIS Spatial Temporal Big Data Store as well. So next popular shapes are, nowadays, hexagons. So the way we create hexagons in Big Data Toolkit is follows. For every single location or point, we use STSHex function to ask, create conceptually 500 meter hexagons, 500 meter sized hexagons, and this function gives us a unique string value that represents 500 meter hexagons. So meaning this point, for example, will belong to this particular 500 meter hexagon somewhere on Earth. Now, we have second function that takes that unique hexagon ID and turn it into actual polygon representation. So now, knowing these two functions, we can do very cool hexagon aggregations. So let's take a look at another one single SQL statement, and it's two-level nested. So if I look at the first one, it's reading text point data set, and it's creating these two columns, hex ID and tip percentage column. Hex ID, I am asking for this particular point or location, create conceptual 500 meter sized hexagon and give me the hexagon ID value. Then I am creating a brand new column called tip percentage, which is the division between tip amount and total amount. The outer SQL statement takes that output and does a little more. So given for each hexagon ID, I am creating new hexagon polygons, and I am averaging out tip percentage column we are creating, and then grouping by hex ID. If I persist this to ArcGIS platform for you to visualize, they look like this. Refresh. Let's turn this off. Actually, let's remove it to be simple and bring it in hexagonal aggregation. Finish. We get to see a bunch of hexagons, but doesn't really tell me anything. So let's symbolize this in a different way. So let's pick graduated colors, and based on new column we created, average percentage, we get to see nice heat map over the New York City area. So darker or intense the color is, and if you drop off the passengers on those locations, it turns out you get some better tips. So the point here is you get to do this cool aggregation and heat map with only one SQL statement, and it only took less than 5 seconds plowing through 34 million records at the same time. Pretty impressive. So, next demo. Let's clean things up a little bit. So let me show you how to do massive spatial join and aggregation. Again, we are persisting 35 million taxi data set and parking it as a taxi table. By the way, this time when we read taxi data, I am doing magic pixie dust operations, which is conceptual spatial partitioning on the fly. Then I have zip code polygon dataset. Each polygon has more than 2,000 demographic variables. So I'm picking those dataset up from this path, and this time that dataset has WKT column, so I am using st from text function to turn well-known text representation into geometry shape information. And again, I am doing magic pixie dust operation to do conceptual spatial partitioning on the fly. And then I am parking that data frame as a zip table. Now I have 2 tables on my hand. I can join them together. So I am selecting all this information by joining 2 tables on this brand new column that I just created. And I am asking for a particular polygon, do you contain a particular point, yes or no? So that's st contains function does. And then I am grouping by this selection that I am interested in. So basically, it will bring up zip code value, zip ID, and each zip code polygon, I will end up seeing summation value, average value of the tip amount, and total population for that zip code boundary, and median household income for a particular zip code area. So, as you can see, the output looks like this. And it took only 32 seconds, by the way, to join 34 million records with about 400 zip code polygons, and each polygon has more than 21,100 variables. So that's pretty impressive that you can all do this in 32 seconds using only 3 worker nodes in the cluster. Then you have this information. You can ask or take it to the next level. Maybe for using built-in Spark ML library, you can do the correlations between the variables to see if there is any distinct standing out relationship going on. Now, again, one thing that I want to highlight is you did not have to create any spatial indexing before you perform spatial joins. Now, before the pandemic, people used to walk on the street, and let's take a walk in New York City area. So let's take a walk on every single street. So we have a function that takes a line geometry, straight line geometry, and as we walk along, it'll give us a point at every 100-meter interval. And if we persist this to the ArcGIS platform, let's see how that looks like. Let's give a few seconds. On the Databricks side, it's done already in 5 seconds. So these are like 100-meter interval points, but at the sky level high, they are very dense. Anyways, with the same idea, let's walk again, but this time, instead of points, let's create hexagons. So, a little different function this time. Hex is along the line, and this time, let's create 200-meter hexagons. And let's persist them on the left-hand side. But in the meantime, once we have hexagons, we want to see the centroid for each hexagon. So let's just do that too here. So it's taking hexes along table we parked in the previous cell, and for each hexagon, we are finding out centroid point out of it. So how nice these SQL statements are, very simple and elegant to use. So let's visualize them. So let's put the hexagon polygons first. And let's bring over the, not this one, actually this one, centroids. Okay, so you will see why we have these many points. What if I tell you, you can now create drive time polygons, a lot of them, in very fast manner. So for those of you who doesn't know what drive time polygon is, for a location, we can ask ArcGIS, show me the polygon or the area where I can drive out to within 1 minute, 2 minutes, and 3 minutes. So these are drive time polygons. We can do them so fast, a lot of them in Big Data Toolkit. So there is now this new function called ST Service Area, where we can give a location and ask for multiple different drive time polygons. So in this one example, I am giving this hard-coded location on Earth, and I am asking service area XY function, give me 3 different drive time polygons, which is 1 minute, 2 minutes, and 3 minutes. So the output is very simple. You get to have 3 different drive time polygon representation in shape column, and you get to see what they are for. Oh, it's for 1 minute, 2 minute, and 3 minute. So in a way, it's OD, origin and destination matrix. So let's go crazy. We have a lot of points in New York City area, and it takes yet another simple SQL statements. From those create number of points in New York City. I want you to take every single point and create drive time polygons and give me 5 of them back. So 1 minute, 2 minute, all the way up to 5 minutes. If I execute this, go over to this side, refresh. It's already done for some reason. Drag and drop. Now, a lot of polygons are coming in. And I can symbolize a little differently. So this time I'm gonna select unique values and I'm gonna select service area cost to color by, and let's select a more distinct color scheme. So a lot of service areas are being rendered. It took 7 seconds to create more than 21,000 drive time polygons. It's very impressive. And the way we do, we are not reaching out to any external web services such as ArcGIS Online or ArcGIS Enterprise. We are doing everything on our own, meaning we are traversing street network on our own internally, and we do it so fast, somehow magically, meaning we can look up node information, edge information, cost information in very fast way for us to traverse on the network so fast. So where I'm getting at, now I have a lot of polygons on my hand. I can ask Big Data Toolkit, can you geo-enrich all of those polygons with business analyst dataset? So basically, I am asking, please do massive business analyst data apportionment with those create number of service area or drive time polygons. So to give you a feel for what they look like, for a particular region, small rectangle that I am creating, I am giving it to as the enrich function, and what it gives me back is more than 2,800 variables, including demographic, consumer spending, market potential variables. So this is one simple example, the output. If I scroll back to the right-hand side, it'll take forever to get to the right-hand side because it's giving me all these create number of demographic variables, consumer spending, and market potential. Now, we can ask Big Data Toolkit to go crazy again. So take those more than 21 drive time polygons, do the business analyst data apportionment on the fly for me. So if I execute this, it'll take about 1 minute and 30 seconds to enrich all those 21,000 polygons all over the New York City area. And if you like, again, beauty of SQL statements, you can combine drive time polygon generation and enrich operations all together into one single statement. Again, 2 levels nested. First, we are creating service area, and second, we are enriching the output, which is drive time polygons. And it takes about the same time, 1 minute and 30 seconds as well. And obviously, the output is a lot of variables appended, enriched to your ArcGIS polygon dataset. Because you have now this many features, we're kind of doing feature engineering as well for you to take your output to the next level to do more advanced machine learning and spatial analytics, if you like, on this ArcGIS platform side as well. So this ends first presentation, and I'm going to pass over to Alex. He will show you how to use Big Data Toolkit in ArcGIS Pro using Jupyter Notebook, and he will show you a cool demonstration using random forest-based tools.
Hello, my name is Alex Hallman, and today I'll be presenting on Big Data Toolkit and Machine Learning in ArcGIS Pro. This demo is inspired by a Kaggle competition. The goal of the competition was to predict the duration of a New York City taxi trip. We will approach this problem by leveraging ArcPy to run a forest-based classification and regression geoprocessing task. Some topics covered in this demo are PySpark SQL, BDT spatial type functions, BDT processors and sources, ArcPy feature classes and table views, ArcPy ML, and ArcGIS spatial data frames. If you want more information on the competition, you can visit this link. I've also directly linked the webpage to the data here. So let's begin by setting up the environment with BDT. So ArcGIS Notebook needs access to 4 items to run BDT. You need to set up the ArcGIS Pro environment with Spark ESRI and ensure that it's installed on this active Python environment. You can do that by using conda in the Python command prompt. For more information on a step-by-step guide on how to accomplish this, visit the link here. You also need a BDT jar file, a BDT Python bindings egg file, and a valid BDT license file. And also you need to ensure that ArcGIS Pro is version 2.6. To begin, we will stop any current Spark sessions running. And then we will set our Spark configuration by giving it the Python files and the jar files it needs for BDT, as well as setting the cryoserializer buffer max value to 128 instead of the default 64. This will allow us to collect more information into memory. Then we start our new Spark session with Spark start, passing in the configuration file. You can also see that I've written a custom time elapse function, which will keep a track of the amount of time it takes to accomplish processes in this notebook. Let's patch the active Spark session with BDT. To do this, you import BDT, and then you do spark.with BDT and give it the path to the license file. This will register BDT and confirm the license is valid. Once this is done, you can confirm that BDT is working by executing this command. Spark.sql, and I'm selecting st from text, a simple spatial type function that converts well-known text format into internal BDT shape struct format. And you can see that it worked without issues here. So now let's prepare the taxi data for machine learning. We will load in the taxi Kaggle data. It's a CSV file, and so we can use spark.read.csv to load it in. We can see the record count is 1.5 million, approximately. You can also see the columns in the dataset. We will be predicting trip duration, but there also exists spatial information. Pick up longitude and latitude, drop off longitude and latitude. Also temporal information like pick up date type and drop off date time. So now let's do some feature engineering. First, we'll enrich the data frame with cosine and sine values of the pickup hour. The motivation behind this is to capture the cyclic nature of time. To do this, first we convert the date time objects into hours, and then eventually get to hours of cosine and hours sine. We append these to the data frame. You can see the result here, hour cosine and hour sine appended to the end. Now we will filter the data frame to only the New York area. We will also filter the trip duration to exclude extreme values. I've arbitrarily defined these values as trips between 2 and 100 minutes long. So we can see the extent chosen here. Let's take a look at those taxi points on the map. So here we have the taxi points, concentrated mostly in Manhattan, but also a little bit in the Bronx and Queens area, some outliers and some points to the local airport. And so we execute those filtering statements, filtering the spatial by spatial and temporal data. And now we have our filtered data set to work with. Next, we'll use our first spatial type function with BDT. That's the Haversine distance. We will enrich the data frame with Haversine distance information. To do this, we create a temporary view of the data frame in Spark SQL, so we can call it here. And then we select ST Haversine distance with the passing in those longitude and latitude values to convert those values to meters. And the meters column is appended to the data frame. Issues with space here as the columns overlaying, but this would be a meters column value. So now we have data, now we begin data exploration and visualization. So we begin by creating a temporary view of the data set, as we did before, to be able to execute Spark SQL. In our first plot, we will plot average meters traveled for each taxi trip, but we will bin it by the pickup hour. To do the binning, we group by the pickup hour, and we use the aggregate function average to get the average meters traveled per pickup hour bin. Then we collect this information into an array, converting the PySpark data frame into an array. Once we have it in an array, we can put it into a pandas data frame. The goal here is once we have a pandas data frame, we can use matplot to plot the information. So let's plot it here. We can see that 5 a.m. had the highest average meters traveled. The early hours, this is consistent with early hours of the morning. Also, there's a small peak in the early afternoon. Now let's plot the total count of taxi trips binned by the pickup hour. Similarly as last time, we're grouping by pickup hour, but now we're taking the count, the total count of the amount of trips in that pickup hour. Same thing as before here. Let's take a look at this plot. Interestingly, 5 a.m. has the least amount of taxi pickups, even though it had the highest average meters traveled. Excuse me. So for each pickup hour, we can see that it increases a little bit in the afternoon and then increases a lot in the evening. For plot 3, we have the total count of taxi trips binned by the log of the duration. It's a little bit different here. Let's take a look at what this looks like. So we can see on the bottom the log of the total duration. And each one of these log duration bins, we have the total count of the amount of trips that had that duration. We can see that it's roughly log normal. However, not quite, because it is skewed a little bit to lower duration values. It makes intuitive sense that there would be more trips that traveled less time than the amount of trips that took longer times to travel. So now let's continue with our feature engineering. Let's rename the columns for convenience to shorten the length. We'll also convert location data to double values and filter the data by the newly added meters per second column, which I add here with column MPS to accomplish that filtering task. This will remove meters per second outliers. So let's do that. We'll print the schema to confirm that everything has been changed to double values here, and also take a look at the resulting data frame with the MPS column appended. So now let's move into part 2. In this part, we will augment the taxi data with New York City zip code data for drop-off and pickup locations. The motivation behind this is to add region-level data with a little bit less granularity for the model to train on. So let's load in that New York City zip code data. This time, instead of using Spark built-in functions, we will use Big Data Toolkit source generic. Source generic will allow us to load in the zip code data and convert those WKT values directly into shape structs in one step. So we can see here we set the options for source generic, that includes the path to the file. Then we call source generic here, spark.bdt.sourceGeneric. And in the select expressions parameter, we have the st from text spatial temporal function. This is also a BDT function, but we can do this all in one step. That converts that WKT values into the shape struct, internal shape struct. So let's take a look at the result. We can see the zip code here, the zip code information. There's 246 distinct zip code regions. Also, we can see that the shape column has been appended. Now let's join the taxi data with the zip code data. This will merge the data together into one data set that we can use to train the model on. So the first step will be to append a shape struct column to the taxi data. We already have that shape struct column here for the New York City zip code data, but we need to do the same for the taxi data. And then this will allow us to use processor point and polygon, and we're going to do it twice. First, we're going to enrich each taxi record with the New York City zip code that contained the drop-off location. And then we're going to do the same for the New York City zip code that contained the pickup location. We're going to remove unnecessary intermediate columns, and in the end, the 3 new columns will be added: pickup region ID, drop-off region ID, and one region, which essentially says whether the pickup and drop-off locations were in the same region or not. So you can see here, we call bdt.processor add shape from XY to add the shape from the longitude and latitude point to the taxi data frame, and then subsequently execute processor point and polygon, bringing in the taxi information and the zip code information. Then we do a little bit extra manipulation here, and we can see the result is now we have the taxi data set appended with the pickup region ID. This is the ID of the zip code that contained the pickup longitude and latitude, and this is done per record. Now we're going to do the same thing for the drop-off region. We execute processor add shape from XY again and processor point and polygon again, bringing in the resulting data frame and that zip code data set. We do a little extra work on the end to ensure that the data types are what we need for model training. We also append a new column, one region, which I mentioned earlier. But this is the binary column that indicates true or false, whether that pickup and drop-off location were in the same region. Then I select the columns in the order that I want them to appear. And so this is the output data frame with the pickup region ID, drop-off region ID, and one region columns. Now we will use BDT processor Web Mercator to convert those lat long values to Web Mercator XY values in meters. So this will be another BDT call, spark.bdt, but this time processor Web Mercator, passing in the taxi data frame, taking that pickup latitude and pickup longitude values and then renaming them, converting them to Web Mercator, and then renaming them to prepare them for ArcGIS. Let's take a look at the schema for our output data frame. We had the entire output from our point and polygon process, now with the shape at X and shape at Y values for ArcGIS. Now we can finally move into our machine learning step. The first task we'll do is split the data into train and test data sets. The validation data set, will be taken from the train data set in the model creation step. So we'll do taxi.random split 0.85, 0.15 for train and test. And now we'll put all of the data from the train and test PySpark data frames into feature classes. To do this, first we will collect the data frame rows like this into an array. And then we will use that array iterable and iterate through them and put them in a feature class. So you can see that here, using ArcGIS insert cursor for each row in that new array. Insert that row into the feature class that we've created here. And it's under this namespace of train. This is the table view namespace for the feature class. We do the exact same thing for the test dataset, collecting it into that array, and then iteratively adding it into a feature class, test feature class. So now that we have two feature classes, test and train, we can use our forward spaced regression on the feature class. If you want more details and information about how Random Forest tool works in ESRI and ArcGIS Pro, you can go here. But quickly, a quick overview. We have our training table view, the training feature class. We also have that prediction table view, that test feature class. So this is the feature class data set that we'll pretend our predictions to using the trained model, and the model will be trained on this. You can see we provide explanatory variables here. These are the variables that the model will be trained on. And so I'm using all the spatial information, like longitude and latitude. Let me scroll here so we can see the whole thing, as well as the hour temporal information, the meters information, and then one region, that binary indicator. And so we provide those explanatory variables as our training variables. We can also set the number of trees to 200 and the validation percentage to 18% of this trained data set to reflect 15% of the original data set. So now we run the model and let's see the results. So on the train dataset, the R-squared was 0.68, which is not bad for a first go. We can also see the variables of importance. Leading the way, meters. Intuitively, that makes sense. By far, the most important predictor. Distance correlating with duration. We also see pickup longitude, drop off longitude, pickup latitude, all here of varying importance. Following that up, our temporal data, as well as the one region. Let's see how it performed on the validation. Similar results. R-squared of 0.68. So now let's see how our model performed on the test data set. So the test data set was augmented with the predictions. And that augmentation created a new feature class called predictions feature class. You can see that if we go back to the ArcGIS code, you can see we specified that here, prediction feature class, predictions. And so that's where the output went for this. So we pull that in here. And to pull in that feature class, I'm now using the ArcGIS library, ArcGIS GeoAccessor .from feature class. Pulls in the predictions feature class into a spatial data frame. A spatial data frame, you can find more information about it at this link, but it's essentially a pandas data frame augmented with spatial capabilities. So I display that data frame here. Let's take a look at some of the predictions. So for lower durations of 120 meters, or for lower durations, we have the duration predicted column. So for lower durations, we have lower durations predicted. And then you can see for those higher durations, original durations here, let's go back. So those 5,927, you can see the predictions are higher as well. So the model is generally following the data, however, not exactly, obviously, which is why R-squared is 0.68 and not 1. So that concludes my presentation. So we would love for you to please provide your feedback for this session by clicking on the session survey link directly below the video. Thank you very much.
Hello everyone, thank you for watching the video. My name is Michael Gayhart. I'm the product manager for Big Data Toolkit, and I also have Kunam Kim, the product lead with me, as well as Alex Allman, a software developer. Thank you for sending in the questions. We will try to get to as many as we can with the time remaining. So let's go ahead and dive in and see how many we can answer. First question about Oracle. For an Oracle DBMS, do you need to install ST Geometry XProc or can SDO Geometry be used? Q, can you grab that one?
I believe this question came up when you saw when we push the output to the SQL Server database. You don't have to do anything. We pick up your Oracle native geometry format automatically on the fly, and we persist geometry information into your Oracle database directly.
Thank you. Next one up, our organization's Databricks supports Python and SQL languages. How do we handle package installation for doing spatial analysis, which is currently showed in the session? Alex, do you want to grab that one?
Right. So in Databricks, you can install Python packages and jar files in the libraries tab of a cluster. So what you would do is you would attach the cluster to the notebook you want to run, go into cluster settings, navigate to the libraries tab, and there you can drop in the BDT jar file and the Python egg file, and then you'll be good to go.
Alrighty, thank you. Next one is about service areas. So how does the service area work? Does it use a road graph? Is it available for any country? Q, do you want to grab that one?
Very good question. The demo you saw, we cover all United States. The source, the road network data set that we used is StreamMap Premium. And the question for other countries' availability, as long as the country has StreamMap Premium available, yes, we can do this street network traversing. As a side note, we are also researching into to see if we can use OpenStreetMap data as well.
Awesome. Okay. The most popular question by likes, I guess, so far is this one. In order to use BDT, does anything special need to be installed on the Spark cluster? Alex, you want to grab that?
Right, so nothing special needs to be installed. However, you do need to pass in the BDT jar file, and you will need an active license file to be able to use it. And if you're using the Python bindings, you'll want to install that in the client side as well. For example, when I said earlier, you'd put the egg file in with the jar file in Databricks. That would be an example of how you'd use it with Python.
Great. Okay. Thank you. Then another popular question, is there any online training provided by Esri? That's a great question. I'll grab this one. You might, a corollary question is, can I search for BDT on Esri.com and find out more information? I do want to make clear that BDT is a product through Professional Services and is not directly on the Esri.com website, but you can always reach out to us at BDT_support at Esri.com, and you can find out more about us there. We'll talk about documentation here in a second as well. But regarding training, in the same vein, there isn't anything available on the Esri.com website, but please feel free to reach out to that email address and we could discuss having a training for your organization. And we will have an announcement that has that email address at the end as well. So if you don't remember that, you'll see that in the announcement at the end. Alrighty, sort of following online with that would be a question about documentation. Will BDT documentation be available in the Git repo? Alex, do you want to grab that?
Right, so we have publicly available BDT docs. I've actually sent the link in the chat as a reply to the question, but I can resend the link again. But yes, docs are publicly available.
Okay, thank you. Next one I have is about Linux. So it says, I assume that the BDT can also apply in Linux. It says in parentheses, of course, with ArcGIS server installed. Q, do you want to?
Very good question. Thank you. Big Data Toolkit runs on top of Apache Spark. So we run anywhere Apache Spark runs on. Apache Spark can run on Linux and Windows as well. Now, the second question about ArcGIS Server, you do not need to install ArcGIS Server. We don't leverage or reach out to any services running out of ArcGIS Server. So BDT, think of it as a standalone product that you can run on your Apache Spark cluster.
Okay, thank you for that. So we've had some more questions come in live. So let's see how many of those. We have a couple more minutes we can get to. So maybe a follow-up on the service area queue. There's a question coming in about, does service area creation work across provinces?
Assuming this question is coming from Canada, I have not tried running this on Canada, but you guys do have StreamMap Premium covering Canada. So yes, it can work throughout or between those provinces. Again, my demo today, I used whole country for United States, so it worked between states.
Excellent. Okay. One for either one of you. Question: does BDT offer all functionality that exists in GeoAnalytics Server?
The short answer, no. There are some common ground in terms of availability-wise, but no, it's not apple to apple. If you become BDT customer and you are looking for something, but we don't have it, BDT is so extensible, so we can create dedicated processors for your own business needs.
Okay, excellent. We'll keep looking for questions in just a couple minutes, but also wanted to ask if there's how this might be integrated, how BDT might be integrated into data science workflows. Alex, is that something you could describe for us?
Right. So anywhere you have access to Spark, Python, you can integrate BDT into your workflow. As long as you have the BDT jar and Python files installed, you can execute BDT to do your spatial joins or any spatial modifications or changes. And then you would just seamlessly integrate that into your data science workflow. One way to do that is converting the output PySpark data frames directly into Pandas data frames. Pandas is a popular tool to use in the data science world, and Spark had noticed that and made that readily available to use. So you can convert it into a Pandas data frame. You can also convert it into a GeoPandas data frame. And Esri even has a Geospatial enabled data frame in their own library. So there are many ways to kind of go in and out of BDT workflow, back into your data science workflow, do some machine learning, come back out, do BDT. So it can all be done sequentially like that. You could even do machine learning in Spark as well. You could use the Spark machine learning packages, or if you want to use the Python packages for machine learning like PySpark or like PyTorch, you can do that too. So many options.
Yeah, wow. That's impressive. Sounds like there's a lot, and I know that data science is a huge area within Esri and our platform. So it's really neat to see how we can integrate in with that. I think we're about at time right now. So just to thank you so much from this whole team for watching. And if you have any more questions, please do send them to us at bdtsupport@esri.com. And with that, I'll go ahead and close it out. Thank you so much for your time.